All right, lads and ladies, welcome back to Calc 1. Last time we had to kind of leave off in the middle of an exam. We rushed it a bit at the end, and I'd like to show you a sort of alternate approach, but we're going to pick up right where we were. So we're going to pick up in section 4.3, talking about how the derivative of a function affects the shape of its graph. That's the name of the game. So let me flip over here to the document camera. Something else you will notice is that thankfully the exams are all finally ended, with a few exceptions. I had a few people whose submissions were, the written work submissions were either corrupted, the PDF wasn't working, or accidentally submitted the wrong PDF. But barring those things, and those people should have received emails from me requesting updated files, the exams are great. So that is nice. This is MAC2311. The section number is 004, which means we're talking about Calc 1. And the date today is the 25th of February, 2022. So today, we're going to finish section 4.3 on derivatives and graph shape. So there are a handful of theorems in this section, but before I dig into any of the stuff that we haven't discussed, like I said, I want to finish that example or kind of work back through that example we talked about on Monday. So last time, the theorem we kind of ended with was, I'll say this in brief, if f prime of x is positive on the interval I, then f is increasing on the interval I. And if f prime of x is negative on the interval I, then f is decreasing on that interval. Right, so if you want to figure out where a function is increasing or decreasing, and this function happens to be differentiable, then one way to do that is to take the derivative of that function, figure out where that derivative is positive, where that derivative is negative. Any x values or intervals on which the derivative is positive will be an interval on which the original function is increasing. Any interval on which that derivative is negative will be an interval on which the original function is decreasing. The example we were looking at, we wanted to find intervals of increase and decrease for, and the function was a fourth degree polynomial, a third degree polynomial, fourth. Yeah, f of x, this is the guy, f of x equals 3x to the 4 minus 4x cubed minus 12x squared plus 5. Okay. So what we did last time was to take the derivative. Because we're trying to find intervals of increase and decrease, we'd like to use this main theorem. When we differentiate this polynomial, we got 12x cubed minus 12x squared minus 24x, which we then factored as 12x times x squared minus x minus 2, which we factored further as 12x times x minus 2 times x plus 1. And the way I proceeded from here was by making a number line. And what I wanted to do first today is kind of go back through the process that takes us from this factored form of the derivative to that number line. I do believe the procedure I showed you is sort of the most efficient way to do this, but there's also an alternate route laid out by the textbook, which I will show for you as well. So Again, what I like to do, and what I would recommend that you do, but it does require a certain amount of comfort with some concepts from pre-calculus, is to take your derivative, having factored it, and make a number line. This number line is going to tell you the sign, positive or negative sign, of that derivative, and hence where your original function is increasing or decreasing. What goes on this number line are the critical numbers for f. Those are the places where f prime is equal to 0 or undefined. So the function f here, being a polynomial, has a derivative which is also a polynomial, meaning it's continuous everywhere, and thus there's nowhere we have to worry about f prime being undefined. So the only critical numbers are going to come from the places where the polynomial f prime is 0, and those are given to us by these factors. So x plus 1, this factor is 0, and x is negative 1. So I'll plot negative 1 over here on my number line. The factor 12x, or if you like just x, is equal to 0 when x is 0. And the factor x minus 2 is equal to 0 when x is equal to 2. And what that does is it chops our number line up into regions. And on each of these regions, f prime will either be positive or be negative. F prime cannot switch from positive to negative anywhere within one of these regions because there are no critical numbers within this region. Right? There are no places where this continuous function, f prime, can change sign between -1 and 0 because he has no roots or discontinuities between -1 and 0. And the same is true for the region from -infinity to -1, the region from 0 to 2, and the region from 2 to infinity. The approach that is taught in pre-calculus that most people go with is to test a point from each region. So you can test an x value from each region on the number line to find the sign of f prime in that region. And in the back of your mind, this is like the fail-safe technique, right? If you, for whatever reason, are insecure or uncertain the sign of f prime in one of these regions, you can always just plug in an x value there. That will work. It'll never lead you wrong. But my goodness, is it a waste of time? You have 4 regions here, right? 1, 2, 3, 4. You could plug 4 x values into this function and one at a time figure out whether f prime is positive or negative in each of these regions. But there is a much faster way to do it. It just requires that you remember a little bit about multiplicities of factors and the end behavior of a polynomial. So let me remind you what the end behavior of a polynomial is. It's like, what do the arrows look like on the graph? So the end behavior for polynomials, it's always one of the following 4 pictures. It's either up on both sides, and any sort of wild shit could be going on in here. Down on both sides, and again, any sort of wild shit could be going on in here. Down on the left and up on the right. Or up on the left and down on the right. Every polynomial graph in existence exhibits one of these end behaviors. And it's very easy to tell which case you're in. These two are associated with even degree. Polynomials, meaning the largest power of x is an even number. And these two are associated with odd degree. Okay, so if you know the degree of your polynomial, that narrows it down to one of the two pictures. The other thing you need is the sign of the lead coefficient. So the lead coefficient is the number attached to the largest power of x, like in this expression for f primed here, the lead coefficient is the number 12. This first picture is associated with an even degree and a positive lead coefficient. The second picture is associated with an even degree and a negative lead coefficient. This guy is associated with an odd degree and a positive lead coefficient, and this guy is negative coefficient. And if you think about it, if f primed is a polynomial, then the end behavior will automatically give you the sign of f primed in the two outermost regions. For example, here, f primed is an odd degree polynomial, degree 3, and the lead coefficient is positive. It is the number 12, which tells me that the end behavior for f primed is this one, odd degree, positive lead coefficient. So that means when you wander really, really, really far off to the left, this thing is guaranteed to be negative. And when you wander really, really far off to the right, this thing is guaranteed to be positive. So just based on the end behavior, I can fill in the sign here and the sign here. In other words, I know based on end behavior that this polynomial will be negative everywhere to the left of -1 and positive everywhere to the right of +2. The other thing that you need is to know how polynomials behave near their roots based on the multiplicity. When I teach this, I call it local behavior near the roots. So that's end behavior. We're going to talk now about local behavior near roots. This is all pre-calc review. It's based on the multiplicity. So if the polynomial p of x has a factor x minus r to the m, then m is the multiplicity. And then I say then x equals r is a root of multiplicity m. And the local behavior, what I mean by that is like the shape of the graph near that root. So roots are x-intercepts. That's the other kind of way to say it. If m equals 1, then the behavior near that root is either going to be, here's r, it's either going to be like this, or is here, something like this. You're going to cross the x-axis. And specifically, you're going to change sign. You're either going to cross from below to above or from above to below, it doesn't matter. If m is 2, then you're either going to look something like this near that root, or like this. You're going to look parabolic, and you're going to bounce off the x-axis. And here there's no sign change. if n is equal to 3, if you have a multiplicity 3 root, again, there's two possibilities, whether you're going from below to above or above to below. It will either look something like this or like this, and you will cross the x-axis. Which again means a sign change. And I'll do one more here, n equals 4. Let's do like this then. It will look like this, kind of like a flattened parabola, or like this. And again, we're going to bounce off the x-axis, so there's no sign change. The basic result is an odd multiplicity root means you're going to cross the x-axis, and an even multiplicity root means you're going to bounce off the x-axis. So if you go over an odd multiplicity root, you're going to change sign. And I drew two pictures here because that means you're either going to go from negative to positive or from positive to negative, right? Either from negative to positive or from positive to negative. Either one is possible. So odd multiplicity means you will change sign. Even multiplicity means you will not change sign. Either you're going to go from positive to positive or from negative to negative, but there's no sign change as you go through that root. Right? Either from negative to negative or from positive to positive. No sign change as you go through the root. This is our quick and dirty review of local behavior near roots and end behavior from pre-calculus. We can apply these to our derivative. For example, this root at -1, that is a root for f prime, comes from this factor, which is a multiplicity 1 factor. So because that is a multiplicity 1 factor, I will either go from negative to positive or from positive to negative. In particular, I will change sign. So since I know from my end behavior I'm negative to the left of -1, I know from the multiplicity that I will change sign as I hop over -1. Right, the -1 comes from this factor, looking like this, right, where n is 1. The multiplicity is 1. The root at 0 came from this factor, which is also a multiplicity 1 factor. So either we're going to go from negative to positive or from positive to negative. I know that I'm positive to the left of 0, and I know that 0 is an odd multiplicity root. So that means I must go from positive to negative. And then we can verify that what we got from our end behavior was correct by thinking about the multiplicity of the root at 2. The root at 2 comes from this factor, which is also a multiplicity 1 factor. So I should change sign. Now I just filled in this minus, thinking about the transition from here to here. And according to the multiplicity rules, I should change sign back to being positive, and that agrees with what I found using the end behavior. So this is my favorite way to do this stuff because it's incredibly fast if you have the factored form of the polynomial. It does require that you remember both of these blue things. And this is about as briefly as I can state those. So if you want a screenshot or something, then go ahead and grab one. This is how I do this. This is how I encourage you to do it. There is, however, a more cumbersome but equally effective way to do it. Besides testing points, you can always also test points. Right? I could have plugged in -2 in this leftmost region to f prime and verified that f prime of -2 is negative, so we're negative everywhere in here. Plug in like -1/2 here, verify that we're positive everywhere here, plug in 1 here, verify we're negative everywhere here, plug in like 3 here, verify we're positive everywhere here. That is the super time wasteful way to do it. Let's go ahead and write down the result, and then I'll discuss the other option. You won't see me plotting points like testing points unless it's absolutely necessary. So the answer to the problem here, we're going to find intervals of increase and decrease. Well, I know that f primed is negative from -∞ to -1 and from 0 to 2. So f is decreasing on the set -∞ to -1 union with 0 to 2. And I know that f primed is positive from -1 to 0 and from 2 to infinity. So f is increasing on that set from -1 to 0 union with 2 to infinity. So the purple here would look like my full solution. This is how I do it, even ignoring this, which is just a. The alternative to the number line no, I should put this in black, I guess. Is what's called a sign chart. And this is where, rather than worrying about the sign of f primed all at once, you worry about the sign of each factor. So if I take f primed equals 12x times x minus 2 times x plus 1, I can build, you'll see this is how the textbook does it. They build a little table for each factor, and they consider each interval separately. So you can put the factors 12x, x minus 2, and x plus 1 over here. And then you can consider your intervals. Now the leftmost critical number, so write down the critical numbers. They were -1, 0, and 2. So that chops the real line up into 4 regions from -∞ to -1, from -1 to 0, from 0 to 2, and from 2 to infinity. And you can kind of ask yourself on each of those intervals, what is the sign of each factor? So from, and then maybe over here I'll add a f primed, which is the product of those factors. From -∞ to -1, x is certainly negative, so 12x would be negative. From -∞ to -1, what about x minus 2? Well, x minus 2 is negative until you get up to +2. So he's also going to be negative. It's kind of like you get to think about just a linear function one at a time. So this would be negative. And from -∞ to -1, x plus 1 is also going to be negative, right? Like imagine plugging in -3 or -2. So if you take this product, negative times negative times negative, you're going to get out a negative. And we do this for each interval. So from -1 to 0, what do we got? Well, x is still negative. We're between -1 and 0, so the factor 12x is negative. X minus 2, if you take something between -1 and 0 and plug it into here, like -1/2 minus 2 would still be negative. But x plus 1 is now going to be positive, right? X plus 1 goes from being negative to positive at -1. So this is going to be positive. So the sign of f prime would be negative times positive. Two negatives multiplied make a positive times a positive is positive. So f prime is positive from -1 to 0. You probably get a feeling for how this works. From 0 to 2, 12x is going to be positive. X minus 2 is going to be negative. X plus 1 is going to be positive. So this is positive, negative, positive, which is negative overall. And then finally, from 2 to infinity, 12x is definitely positive. X minus 2 finally makes the flip to being positive, and x plus 1 has been positive. So this is all three factors positive. Primed is overall positive. I'm not a big fan of the sign chart, but it does work, and some people like it more. So, you know, if that's how you feel, if you prefer doing the sign chart, nothing wrong with that. I would say practice maybe each a little bit. Find one that feels more natural to you, and then do most of your practice that way. So pick one and kind of stick with it. That way you develop the skills and get confused. So this is sometimes called the ID test, or the increasing decreasing test, where you find the sign of f primed to determine where f is increasing or decreasing. We can do one more example like this, but then we're going to talk about something related to the second derivative. Let's see if we can find something a little more exciting. Well, maybe we should move on. Yeah, let's try. Let's take a peek at number 18 here, x to the 4 e to the negative x. We're just going to do the increasing decreasing part for now. We're going to apply the same theorem we just did. We're going to take the derivative and try to find where that thing is positive and negative. This derivative requires a combination of product and chain rules. So first I will differentiate the x to the 4 and leave the e to the negative x alone. That gives me 4x cubed e to the negative x. And then I'll add that to what I get when I leave the x to the 4 alone and differentiate e to the negative x. That'll give me e to the negative x times -1 by the chain rule. Factoring out e to the negative x, I get 4x cubed minus x to the 4 times e to the negative x. And from that polynomial piece in the front, I can extract a factor of x cubed, leaving me with 4 minus x e to the negative x. It's worth observing that this factor is always positive. Strictly positive, right? Never even equal to 0. So when it comes to sorting out the sign of f primed, I only need to concern myself with these polynomial factors. Both of those factors are odd multiplicity. The roots are at 0 and 4. If you think about the expanded form of those polynomial factors, the dominant term is the x to the 4. This would be a 4th degree polynomial with a negative lead coefficient. So that tells me that we are negative here and here. And as we hop over the root at 0, him being an odd multiplicity 3, we will change sign there. And we can verify that this should be negative because we should change sign as we hop over the multiplicity 1 root of 4. So we're done. All right, so fast. Thus, f is decreasing on negative infinity to 0 and 4 to infinity. F is increasing on the interval 0 to 4. That's super fast. Question. Suppose f is continuous at x equals c and that f changes. I'll give you two different possibilities here. F switches from increasing to decreasing at x equals c. I'll leave a little bit of space there. And we'll consider the other possibility. F switches from decreasing to increasing at x equals c. So the hypothesis that f is continuous at c, together with either 1 or 2, will force a specific behavior or feature on the graph at x equals c. Think about this guy. If I'm decreasing until I get to 0, and then I turn around and start increasing, what sort of feature on the graph must exist at 0?
A minimum?
Yeah, there must be a local min. Right? If we switch from, that's the picture down here. Here, see if I switch from decreasing to increasing at x equals c, then f has a local min at x equals c. I can't say whether it's an absolute min or not, but I can definitely tell you that there is a local min there. And the other thing that could happen, right? If we're switching from increasing to decreasing, if you're going up, 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 and then you turn around and start going down, 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 then f has a local max at x equals c. Picture here. Something like this. This is called the first derivative test. So that's the name for this rule or system here. If you switch from increasing to decreasing at some number, then you must have a local max. If you switch from decreasing to increasing at some number, then you must have a local min. Sorry, my wife just called me and I paused him and then she called again. I'm so sorry. Sorry about that. So yeah, this is called the first derivative test. We do require this hypothesis that the function be continuous because it is possible to switch from increasing to decreasing without rolling through a max. It is possible to switch from decreasing to increasing without rolling through a min. So we require f to be continuous at x equals c to avoid stuff like this, right? Here is a function that switches from increasing to decreasing at c. But there's no local max there. And that function blows up to infinity at c. You've got a vertical asymptote. But the thing works the way it feels like it works. If you have a connected graph and you're going uphill and then you transition to going downhill, you had to have rolled over the top of a little peak. And we do not require that f be differentiable at c itself. That's kind of the nice thing, is that this will work okay for cusps. Even if the graph is not smooth at c, as long as it is connected at c, this logic is still sound. So we could return to this previous example and say, find me any local mins or maxes. We can say now, any local extremum for f of x equals x to the 4 even negative. And we would say by the number line work above, or you could cite your sign chart. Again, I like the number line because I think it's a nice visual way of representing these things that is pleasantly intuitive and very fast. By the number line above, f has a local min at x equals 0 and a local max at x equals 4. And if I want to know the min value or the max value, I would have to plug those x values into the original function. So here I could say the min value is f of 0, which would be 0 times e to the 0, which is 0. And the max value is f of 4, which would be 4 to the 4, which is 64, times e to the negative 4, which I don't know, is just e to the negative 4. In other words, we know the points, right? The local min is at the point 0, 0, and the local max is at the point 4, 64 e to the negative 4. Generally, I do find it rewarding to look at the graphs here, and also helpful down the road. where we're going with this is we want to be able to sketch nice graphs by hand without a graphing calculator. So here he is. So here's our local min at 0, 0. Here's our local max at 4, 64, e to the negative 4. And you can verify that y value is 4 to the 4. Oh, 64 is 4 cubed, isn't it? I'm sorry. What is 4 to the 4? It'd be 64 times 4 is 256, right? So sorry. Most of the time, the first derivative test is going to be your best friend when it comes to identifying local extrema, because usually that's a part of a procedure where you're trying to do other stuff, like find intervals of increase and decrease. There is another tool for identifying local extrema if all you care about is finding local extrema. You're not also trying to find intervals of increase and decrease, called the second derivative test. But before we talk about the second derivative test, I want to kind of explain to you what the second derivative tells us geometrically about the graph of a function. So in the same way that the first derivative of a function tells you whether that original function is increasing or decreasing, the second derivative tells you whether the first derivative is increasing or decreasing. It's just a restatement. If a function's, avoiding notation here, if a function's derivative is positive, then that function is increasing. And if a function's derivative is negative, then that function is decreasing. So what if that function is the first derivative of some other function? This would say if f double primed of x is positive, then f primed of x is increasing. And if f double primed of x is negative, then f primed of x is decreasing. Right, because f double prime is the derivative of f prime. And the fun game here is to kind of ask yourself or try to figure out, what does it look like to say that f prime is increasing or f prime is decreasing? And obviously there's 4 cases here, right? So we're talking about permutations where f is increasing or decreasing, and f prime is increasing or decreasing, and then f is increasing or right? So I said that a little bit wrong, but let's sketch some pictures. Let's assume f is increasing and consider f prime increasing and f prime decreasing. Well, if f is increasing, that means all the tangent slopes are positive. And then we're going to consider these two cases separately. F prime is increasing, and maybe I should have said or. F prime is decreasing. If f prime tells you the slope of the tangent line, and f prime is itself increasing, that means the slopes of the tangents are getting steeper. The slopes of the tangents are themselves increasing. And if f prime were decreasing, that would mean the slopes of the tangents are themselves decreasing. So I'll try to draw these two pictures for you by kind of iterating little tangent slopes and see if you can suss out the shape of the graph, and then I'll tell you the names for those shapes. If you took college algebra way back in the day, and you heard this as increasing at an increasing rate or increasing at a decreasing rate, which is just god-awful terminology. I'm so glad we got rid of that shit. So here I will draw for you two pictures of increasing functions, i.e. cases where f primed is positive, one of which will have f primed itself being increasing, and the other one will have f primed itself being decreasing. In other words, these two pictures will both correspond to f prime being positive. One correspond to f double prime being positive. One correspond to f double prime being negative. Okay. And I'm just going to iterate little tangent slopes. So I'm going to chop this up into a few intervals, like so. And we say these, so this is going to be f increasing and f prime increasing. We'll start here with a little tangent slope. And we're just, f is increasing, right? That means we're going uphill. Like that. And we'll say, here's my first little tangent slope. That's a positive slope. Since f primed is increasing, that means the slopes of tangents are themselves increasing. So the next little tangent slope needs to be steeper. And the next little tangent slope needs to be steeper still. And the next little tangent slope needs to be steeper still. This is going to yield a curve that looks something like this. Which we call concave up. That's the name for this. So f increasing means f primed is positive. F primed increasing means f double primed is positive, and we call this concave up. Because the fact that your tangent slopes keep getting steeper, forces the curve to have this, I forget my image is mirrored, is like this. The graph gets steeper and steeper and steeper and steeper. Now I'll draw a curve where f is increasing and f primed is decreasing. Now again, because f is increasing, all the tangent slopes have to be positive. None of these tangent slopes can point down. I start with something like this. There's a positive tangent slope. And then I have something like this. That's also a positive tangent slope, but the slope has decreased a little bit. Here's another positive tangent slope, but again, the slope is decreasing. Here's another positive tangent slope, but again, the slope is decreasing. And what you see is a shape something like this. So the fact that f is increasing means f primed is positive. But the fact that f primed is decreasing means that f double primed is negative. And we call this concave down. And both these curves are increasing functions, right? So this is increasing concave up. This is increasing concave down. You can also have decreasing concave up and decreasing concave down. This would be, I should say, increasing concave up. This is increasing concave down. And without going through so much hullabaloo, here is decreasing concave up. This would be f primed is negative, f double primed is positive. This is decreasing concave up. I don't know if they hyphenate these or not. Concave up, concave down. And then decreasing concave down. Think about for a second. Would look like this. This means f primed is negative and f double primed is negative. This is. And these four basic graph shapes can be thought of as sort of the building blocks for all of your typical smooth curves. Increasing concave up, increasing concave down, decreasing concave up, decreasing concave down. The way I think of it is that concave up holds water. If you pour water into a concave up shape, it will hold it. Concave down, water runs off of it. And if you poured water on top of this, water would run off. The sense in which this is useful for your min-max games is that if you have a critical number, a place where the tangent line is horizontal, say, and you know your concave down there, there's only one possibility. That's got to be a max, right? And if you have a critical number and you know your concave up there, there's only one possibility. That's a min. This is called the second derivative test. So before I state that, let me just be very, very clear about this. Just like increasing and decreasing, if f double primed of x is positive on the interval I, we say f is concave up on I, and if f double primed of x is negative on the interval I, then we say f is concave down on that interval. Let's go ahead and introduce our second derivative test, which is more or less what I just tried to show you or convince you with my hands, but we'll make it more formal. The second derivative test has a little bit of an extra hypothesis. Theorem. If x equals c is a critical number for f, and f double primed of x is continuous at x equals c, then f double primed of c being positive means that f is concave up at c. But if you're concave up at a horizontal tangent line, then f must have a local min at x equals c. And if f double primed of c is negative, then f is concave down, which means that f must have a local max. This is called the second derivative test. And it is sometimes a bit faster than the first. So let's look at maybe number 19 there to start. Minus 3x squared plus squared. And we have a choice here whether to use the first or second derivative test. I will go ahead and use the second derivative test. We've already done an example of the first. We know that using the first derivative test means building a number line or a sign chart for f prime. Here I just calculate f prime. The 1 differentiates to 0, 3x squared differentiates to 6x, and 2x cubed differentiates to 6x squared. Factoring out 6x, we get 1 minus x left. So the critical numbers are x equals 0 and x equals 1. And I could pretty easily use end behavior and local behavior near roots to cook up a number line for f primed. But if I'm feeling exceptionally lazy, I can just calculate f double primed as 6 minus 12x. Since f double primed is continuous everywhere, it's a linear function, I know that f double primed will be continuous at those two critical numbers. And this has f double primed of 0 equal to 6, which is greater than 0. So since I know f has a horizontal tangent line at 0 and f double primed is positive, I know that at 0, this function looks like this. Horizontal tangent line and also concave up. So that means f has a local min at x equals 0. And if I compute f double primed of 1, that's 6, where's that double prime? Sorry, 6 minus 12, which is negative 6, which is negative. So I have a horizontal tangent line and I'm concave down. Well, that means this must be a max. Oh, sorry, not at x equals 0, at x equals 1. X equals 1. So the skinny of this is, if you don't care about finding intervals of increase and decrease, all you care about is finding local mins and local maxes, the second derivative test will be faster provided your function is easy to differentiate and the second derivative is continuous. Functions that fall into this category cleanly and neatly are polynomials, of course. Any polynomial will have all derivatives continuous, and they're super easy to differentiate. And when you take higher derivatives, they become easier to work with because terms go away. So if you're just looking for local extrema of a polynomial and you don't care where the function is increasing or decreasing, then I wholeheartedly recommend the second derivative test. If you are looking for intervals of increase and decrease in addition to local extrema, then don't waste time taking the second derivative. Just build your number line for f primed. These are also good sources of kind of fun concept questions. So if we look in the textbook to stuff like these, 27 through 31, this sort of stuff. They say sketch the graph of a function that satisfies the following conditions. These require comfort with the second derivative test. Or things like this. Suppose f double prime is continuous everywhere. If f primed of 2 is 0 and f double primed of 2 is negative 5, what can you say about f? Well, since f primed of 2 is 0, you know you have a horizontal tangent line at 2. Since f double primed of 2 is negative, you know you're concave down at 2. So if you have a horizontal tangent line, concave down, local max. Or here, if f primed of 6 is 0 and f double primed of 6 is 0, ooh, that doesn't live in this, does it? So let's talk about that. There is a possibility that exists outside of this theorem. Places where you transition from increasing to decreasing or decreasing to increasing have special names. Those are local mins or local maxes. And the second derivative test allows us to catch local mins and local maxes. There's also a special name for where your second derivative transitions from positive to negative. Those are called points of inflection or inflection points. So an inflection point on the graph y equals f of x is a point where the graph changes concavity, meaning you go from concave up to concave down, or from concave down to concave up. Right? And this IE means there is an inflection point, which from here on I will abbreviate as IP, at x equals c if f double prime switches sign at x equals c. Goes from positive to negative or negative to positive. Inflection points are detected precisely the same way the first derivative test detects mins and maxes, only you do it with the second derivative. So you make a number line for the second derivative and see where that thing changes sign. And you could, in theory, develop maybe a third derivative test for inflection points using similar principles that the second derivative test uses to detect mins and maxes. We won't go into that. We're just gonna chill at this. So let's see if we can find some inflection points. Let's give ourselves a neat function, maybe something like number 12 here, x over x squared plus 1. Find any mins, maxes, and intervals of increase and decrease, and points of inflection, and intervals of concavity. These tend to be quite long problems. I don't think we'll have time for another after this. So let's make it count. Find intervals of increase and decrease, local extrema, intervals of concave up and concave down, and inflection points. You see why we want to have abbreviations for these things. For the function f of x equals x over x squared plus 1. So for the first two things, intervals of increase and decrease and local extrema, I need the first derivative test, right? If I only cared about local extrema, maybe I would jump to the second derivative test, but they've also asked for intervals of increase and decrease. So there's no sense in wasting time. We just go to the first derivative test. So f primed here, we can calculate it using the quotient rule. There's no harm in that. That's the bottom times the derivative of the top. Minus the top times the derivative of the bottom divided by the square of the bottom. So that's x squared plus 1 minus 2x squared all divided by x squared plus 1 quantity squared x squared minus 2x squared is negative x squared. So this is 1 minus x squared over x squared plus 1 all squared. Nothing cancels here, but you can factor the top. The bottom doesn't factor. X squared plus 1 is an irreducible quadratic. But the top can be factored as 1 minus x times 1 plus x. And that denominator is just stuck. He's x squared plus 1 all squared. So there's your first derivative. And as useful a form as you could possibly take. Critical numbers would be places where f primed is 0 or undefined. Graciously, the denominator here again is an irreducible quadratic. The roots of x squared plus 1 are non-real complex numbers, positive I and negative I. So he will never be 0, so f primed is never undefined. But f primed will be 0 at x equals 1 from this factor, and at x equals negative 1 from this factor. So I draw my number line for f prime, and I place on it the two critical numbers, positive 1 and negative 1, of course in order. This chops my number line up into 3 regions. And we observe that the denominator here is always positive. So I can use the end behavior multiplicity game just by thinking of the sign of the derivative as coming from the sign of the top. The top is a degree 2 polynomial with a negative lead coefficient. So from the end behavior of the numerator, which is down on both sides, right? Even degree, negative lead coefficient. So this bad boy is going down on both sides. This bad boy is always positive. And then using the multiplicity trick with the factors of the numerator, I can verify that I should jump sign as I go from here to here. Verify that I should jump sign going from here to here. It matches with what I got by the end behavior. So we were decreasing, then increasing, then decreasing again. And here's another reason I like the number line notation, because I can just write in here, okay, there's a min there, and there's a max here. And it's just, I like it. It kind of gives me the whole story in one picture. That's quite easy to come up with. When x is negative 1, the function value here is negative 1 divided by negative 1 squared plus 1, which is negative 1 over 2. So this point is negative 1, comma, negative 1/2. If I plug positive 1 into this function, I get 1 over 1 squared plus 1 is positive 1/2. So I have a local min at negative 1, comma, negative 1/2, and a local max at positive 1, comma, positive 1/2. And I also get my intervals of increase and decrease. F is decreasing from negative infinity to negative 1, unioned with positive 1 to infinity. F is increasing on the open interval from negative 1 to 1. Look at that, we knocked out the first two parts of this problem in just like 2 minutes. Dope. To move on from here, I need the second derivative. And it is the case that that's a little less pretty than this guy, right? Because we got to differentiate this guy. I would go at it from this form rather than the factored form, because if you try to differentiate from here, you're going to need some product rule every time you hit the derivative of the top. Here you don't. So we found intervals of increase, local mins, local maxes. We find intervals of concave up, concave down, and inflection points. I need the second derivative. So that's the bottom times the derivative of the top. That's x squared plus 1 squared times the derivative of 1 minus x squared, which is negative 2x, minus the top, 1 minus x squared, times the derivative of the bottom. That's a chain rule thing. That's 2 times x squared plus 1 times 2x, all divided by the square of the bottom, which is x squared plus 1 to the 4. And this might look hideous and scary, and a little bit. But if you think about your algebra strategically, it's not going to be that bad. Look for common factors. There's an x squared plus 1 squared here. There's an x squared plus 1 to the 1 here. So between the two terms upstairs, here's one term. Here's the other term. Between those two terms upstairs, I can pull out an x squared plus 1. Only one of them because this only has one to give. I can also pull out a 2x, maybe a negative 2x. Let's do it one step at a time. So if I simplify what's left over here, this is negative 2x times x squared plus 1. And then minus 2x times 2 is 4x. This x squared plus 1 has been factored out times 1 minus x squared. And all of that being divided by x squared plus 1 to the 4th power. I can extract a negative 2x from what remains, and I think that's the way to go. There's no other common factors in the numerator. So after that, we will have to distribute things out and combine like terms. I'll have x squared plus 1 times negative 2x times, let's see what's left upstairs. Factoring this out, so I'll just have x squared plus 1 there. Pulling out negative 2x, so this piece will become a plus 2. And then I've got my 1 minus x squared still chilling. And downstairs, I still have my x squared plus 1 to the 4th power. So be strategic about your algebra, right? Don't just make moves without thinking about them. You do need to make moves, but try to plan ahead. I can cancel the x squared plus 1 here with one of these powers down here. I can distribute the 2 in here and combine like terms. So I'll have 2 minus 2x squared. So what I'll get at the end of the day is negative 2x times, let's see, x squared minus 2x squared. And then 2 plus 1. So what is that? That's negative x squared plus 3 over x squared plus 1 cubed. So here is our nice fully simplified second derivative. This piece is a difference of squares. This is negative 2x times 3 minus x squared over x squared plus 1 quantity cubed. And now for my last bit of simplification. Doesn't look like a difference of squares, but it is. That's root 3 minus x times root 3 plus x. And this is now the most useful form of this second derivative. Not a small amount of work, I can see. The places where f double prime can change sign are 0 from this factor, root 3 from this factor, and negative root 3 from this factor. As in the first derivative, this bottom is never going to be 0. So I construct my number line for f double primed. Negative root 3, 0, and positive root 3. And on each of these intervals, f will either be concave up or concave down. And if f double prime changes sign at any of these numbers, those will be x values of inflection points. From, say, this form here, again, the denominator is always positive, not because it's a square, but because x squared plus 1 is always positive. From here, you can see that the numerator is a degree 3 polynomial with a positive lead coefficient. If you distribute this negative 2x, you would get positive 2x cubed minus 6x. So degree 3, positive lead coefficient, that means we're going down on the left and up on the right. And then again, each of these factors is an odd multiplicity factor. So I will change sign, I will change sign, and that is consistent with what I get from my end behavior. So this is an IP, this is an IP, and this is an IP. Because we are over time, I will not go ahead and find the y coordinates here. Let's just write down the result. F is concave down on negative infinity to negative root 3, union 0 to positive root 3. And f is concave up on negative root 3 to 0, union with positive root 3 to positive infinity. And if you'll allow me, I'll take 10 seconds to verify this in Desmos, because this is quite a cool graph. This fellow is sometimes called a serpentine. There we go. This thing is sometimes called a serpentine. And if you plot the points of interest, we had -1, comma, -1/2. Right there, there's your local min. Turns out to also be an absolute min. 1, comma, +1/2. There's your local max. Turns out to also be an absolute max. Your inflection points should be at negative square root 3, comma, something. That thing is f of negative square root 3. There it is. There's your IP. At 0, comma, f of 0, which is 0, you have another IP. And then at square root 3, comma, f of square root 3, we had another IP. If I play with these scales a little bit, you'll see them slightly better. Let's take this from like -1 to 1. Negative 10 to 10, something like that. I was -5. There we go. Okay. So you see over here, we are decreasing concave down. We switch to decreasing concave up in here. We switch to increasing concave up. Increasing concave down, decreasing concave down, decreasing concave up. All of those neat features. You may be able to smell it, but if I told you all of these mins, maxes, inflection points, and also maybe the horizontal asymptote, you could draw a pretty dope graph of this function. In fact, you could draw exactly this graph. You could draw a perfect graph of this function if you had that information. Intervals of increase, decrease, intervals of concavity, mins, maxes, inflection points, and long-term end behavior, aka horizontal asymptotes. This is why the next section in the textbook, 4.4, is all about limits at infinity, not explicitly limits at infinity, but L'Hopital's rule in indeterminate forms, which is kind of the last major tool you need to be a really good hunter of horizontal asymptotes. because the following section 4.5 is about conjuring these graphs by hand from the information we just cooked up here. Those problems tend to be long problems because you got to do all the shit that we just did over here on the dot cam, then find some limits, then draw a graph. So practice this homework set earnestly. I know it's a long homework set. I trimmed it as much as I could because I really don't want you to feel compelled to rush or, you know, Symbolab or whatever, any of it. I really do want you to solve those problems. If you're having a hard time with any of it, don't hesitate to ask for help. Take pictures of your work, send it to me, come by office hours, all of that stuff. Tests are graded. If your test wasn't graded, please take a look for some feedback in there. Also, take a look at the feedback either way. I'll say just this one thing and then I'll let you guys go. There were 3 folks who I know copied answers from each other. I haven't tried to seek hard evidence of this. And I think in this instance, because those answers that were copied were wrong, I may not seek hard evidence in this instance, but you know who you are. And I want you to know that I know who you are. And I want you to know that your name is on a list. And if I see anything sus in the future, it's a conduct trial. Don't do that shit. All right, please, please, please don't do that shit. I don't want that shit. You really don't want that shit. You're not as sneaky as you think when you do that stuff. So please, 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 for the love of God, don't do that shit. But that's it. If you want to talk to me about test grades, anything like that, office hours is the place. You can canvas message or email. You guys know the drill at this point. Work hard on that homework, and I'll see you all on Monday. Take care.